The singular value decomposition is known in statistics as principal components analysis. In fact, one will often see the acronyms SVD and PCA used interchangeably. There are two sides to this. One is the idea, geometrically, of moving ellipses, or I should say ellipsoids, in higher dimensions. The other is the idea of fitting data to a plane. So these are actually, both of these statements interact in a very concrete way with the singular value decomposition. I'll talk first about moving ellipses. So here's a basic geometric fact which SVD verifies for us. Suppose we have an ellipse. It has an overall center somewhere, and it has a minor and major axis. Now, geometrically, we have the sense that you can do a certain procedure to normalize this ellipse. First of all, you can move the center, so let's do translation. You can translate so that the center of the ellipse is at the origin. Then you can rotate so that the ellipse is aligned with the axes, so that the major and minor radii or major and minor axes of the ellipse are aligned with the actual axes of your coordinate system. And finally, you can stretch or shrink to move the ellipse back to the unit circle. So let's think about what an ellipse actually is. As an equation, say in two variables, an ellipse is given by something of the form ax squared plus bxy plus cy squared equals d. Now there are conditions in what a, b, c, and d can be, and we'll come to that. We can view this as an equation in linear algebra in the following way. Notice that the left-hand side of the equation is expressed can be expressed this way. It's a form of inner product using a symmetric or Hermitian matrix A, B over 2, B over 2, C, and treating x, y as the inputs. After all, we'll get x times A, y times B over 2, and x times B over 2, y times C. If we combine those vectors with x and y, we get the x squared term, the xy squared term, the y squared term, and the cross term with an xy appearing twice. And this equals d is another way of saying that expression. So let's work under the assumption that this matrix, let me perhaps call this S, being symmetric or Hermitian. Let's suppose that this matrix has, let's say, positive eigenvalues. By the spectral theorem, we already know that it has real eigenvalues. So the only question is if those eigenvalues are positive, negative, or zero. By the way, when I wrote down this equation, I actually implicitly applied the translation. Translation is not very interesting, right? That's just saying x moves to x minus x naught, and y moves to y minus y naught. So the translation, you can simply find the center and do a coordinate transformation back. So you might have x minus x naught, y minus y naught in these different expressions here. So in fact, this equation refers to any ellipse centered at the origin. So in this problem of moving ellipses, how does the singular value decomposition come into play? Well, it comes into play in the sense of how we interpret its proof. Because S is a Hermitian matrix, you know that there's a unitary matrix V such that V diagonalizes the matrix. This is, of course, the spectral theorem. So what is V after all? It's a basis. It's an orthonormal basis. So columns of V form an orthonormal basis. That means that overall V is a combination of rotation and reflection from the original coordinate system to one where S becomes D. Of course, that's sort of shorthand, but what we're saying here is the following. In our original coordinate system, the matrix S is representing some ellipse. And if we apply this rotation represented by the orthonormal basis V in the basis V1, V2, which are really these vectors, of course, the ellipse is aligned with those two directions. By the way, a brief note, in the previous slide I used D as just a number. Here, of course, D is a diagonal matrix. That's perhaps a bad use. Maybe I ought to call this V sigma squared, knowing what we know about SVD. Okay, now, in fact, this structure tells us even more, because, of course, the matrix sigma is sigma 1, sigma 2, dot, 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 sigma n. And indeed, if we rescale these distances by the sigmas, that's exactly what it takes to shrink the ellipse back to the circle. So, in fact, what we're saying here, what is the equation of this ellipse? It would be, in the coordinate system V1, V2, it would be x over sigma 1 squared plus y over sigma 2 squared equals 1, the standard equation of an ellipse, centered at the origin with major and minor axes sigma 1, sigma 2. So what we're doing is we're saying there's a rotation that takes the matrix A, B over 2, B over 2, C, and translates it to sigma 1 squared, 0, 0, sigma 2 squared. And that's what's reflected when we change the equation ax squared plus bxy plus c equals some constant to this equation. I'll leave it to you as an exercise to see exactly how the equations and the constants change this transformation. To do so, rely on the fact that the original ellipse is expressed as a Hermitian inner product of xy with itself. So we're using the norm defined by S and diagonalizing it.